Greetings and welcome again. We are going to the third part of the Unit 2 of Robotics and Automation. Okay. We have already seen the syllabi. In this, we are going to talk more about the precision and accuracy of a robot. We are going to also look at the end effector and the grippers. Okay. So let's move on. This is a continuation of the or a summary of what we had done last time. We had talked about the various configuration of robots: the Cartesian robot, the cylindrical robot, polar or a spheric robot, and then we have the Scara robot or the angular robot. Okay, the different configuration we have seen. Now, coming to the accuracy and precision, these are the interview question where the it could be a famous question asking to differentiate you between what is the difference between an accuracy and our precision. Precision is the degree of closeness to the measurement with each other. Okay, how precise? Okay, can you see here? These things are all highly precise now. But accuracy is the closest to the value. Now, if I come to the green point, then I am very accurate to the bullseye. Now, precision is a degree of closeness or measurements with each other. Then precision often referred to as repeatability. Now, trying to come to the same point again and again is the word repeatability, or it is also called as reproducibility error. Okay, precision is getting consistent result of repeated measurements. Now, but what is accuracy? It is the degree of closeness or measure to the of the measurement to the target or the reference value. Now, accuracy is often referred as bias error, and accuracy is measuring near the target or true to the reference value. Now, this is what is the difference between accuracy and precision. Now, again, come to the famous example that people give as the dart here. Accuracy refers to how close a measurement is to the true or the accepted value. This is very accurate as well as precise. Everything is near, and even the second or the third reading is also third or four readings are also as close. Here, the four readings are close, but then they are out of the point of truth, then that is not accurate, but it's precise. Now this is here this one is neither accurate nor it is accurate. Yeah, sorry, it is accurate, but it is not precise. It's all coming towards the center point, as trying to be near, but it is not precise. Whereas here it is neither accurate nor precise. Everything is out and scattered around. So that is the last type of the example on accuracy and precision. Now, defining what is the industrial robo. Industrial robotics is the use of robo for manufacturing or other industrial process, including assembly, packing, labeling, painting, inspection, testing, welding, and other similar processes that we use in the industry. The use of robo for these tasks should provide high endurance, okay, and precision and speed for the tasks. Now, high endurance is that in whatever it should not get changed between the first value and the second value. Okay, it should be able to withstand all the various challenges that comes in the atmosphere of that environment where the robo is being used. Now, on the configuration purpose, coming back again, we have the orthogonal or the working. This is also called as the gantry robo or the Cartesian coordinate robo. Okay, this is the cylindrical and its cylindrical working area where it is about a pedestal and is able to move up and down, and it's also able to go up and down. Okay, then you have the joint robo or sphere coordinate robo. You have the assembly robo or the Scara robo. Now this is the example of you see the picture, you see the gantry robo here where it can move horizontally, it can move up and down, plus it can also try and then have the component lifted up, etc. etc. Okay, the gantry type or a traverse type. The same thing is shown in the drawing. It is all everything is linear. Okay, shown as linear movement up, or this can slide again here and then here this one. Then the cylindrical coordinate system, this can swivel about this point, about the axis, plus this can move, slide up and down, and the entire thing can go again linear up and down. Right? The polar coordinate, where we have the one rotation plus one here another rotation is there, and then this can move up and down here. The next one is the articulate robo, where we have all the three things can all the three axes can rotate about its axis. The standard notation symbol, what we use is that for rotation we put it as R, for the other one we put it as L. Okay, and the different axes is shown here. The notation is 3R. SCARA stands for selectively compliant assembly robo arm, or SCARA. Then it's similar to a jointed arm robo, except that the vertical axes are used for shoulder and elbow joints to be compliant in the horizontal direction for vertical insertion of task. Now here, this is, instead of R, they put it as a V and a O here. The manipulator joints are shown like this, how the joints are there, how the movement takes place in the manipulator. The translation one, where it can slide up and down here, is a linear type or a orthogonal type. Okay, so this is exactly when this moves, this is exactly perpendicular to this. You also have the rotary motion. In the rotary type, you have the R type or the twisting type here. This is the twisting type, and then you also have the revolving type. Okay, so three different types of rotary motion: rotational, twisting, and revolving joint. Now the grippers are shown here. In the grippers, you see the various types of grippers are shown. I have another picture here. Now this grippers here are like this. Depending on what is to be gripped or what is to be held, you can change the shape of the gripper. So it is custom made for different applications. Now, there are types of grippers. There are mechanical grippers consist of two or more fingers that can be actuated by a robo to open or close the grasp. Okay, you have the vacuum grippers in which the suction cups are used to hold flat objects. Okay, but this is being used for lifting glass sheets of glasses in a glass factory, uh, or even in a automobile factory, the assembly of the front dashboard glass. Magnetized devices for holding ferrous parts, adhesive devices where adhesive substance is used to hold flexible materials such as fabric, etc., or simple mechanical device such as hooks. You can use it here. Envelope, we'll introduce you in this in this episode about what is the envelope. A work envelope is defined as how far the robo arms or end effector mounting plate can reach vertically, horizontally, and backward. Can we see the this area here, or this volume? Now this is the place where the end point of the robo can can reach all these places. The dimension do not include the additional reach granted by the tools, because that cannot be predicted. You can make the tool much longer or shorter, so that is not comes under the envelope. Any unreachable area beyond the work volume or in within that is called as the dead zone, where the robo cannot reach to that place. Let's summarize and then close this episode. We looked at what is the difference between precision and accuracy. We looked at the various grippers and the types of grippers, the mechanical grippers or the hydraulic grippers, etc. There, the work volume or the work envelope or the work volume. In the next episode, we'll talk more about the operation envelope. Okay. Thank you very much. We will stop here.